In the darkness between distant stars, a question hangs like a faint echo that never quite fades. How can there be a beginning when time itself is part of what begins? How can space unfold out of something that has no size, no shape, no before? The modern story of the universe starts with a single phrase that sounds simple and complete, the birth of the cosmos in a great expansion, often called the Big Bang. According to the equations that describe gravity on the largest scales, there is a moment when all the matter and all the energy that ever will exist is compressed into a state so dense and so hot that ordinary language begins to break apart. In that state, the concept of a clock ticking has no meaning. There is no distance to measure, no before and no after. Time and space appear together as if they are two aspects of the same event. The usual instincts of the human mind push back against this idea. Every story that mind has learned follows a chain of causes and consequences. A child learns that a seed grows into a tree, that clouds gather before rain, that a spark lights a fire. The thought of something that simply begins without a cause, without a previous step, feels incomplete. The question rises again and again in quiet rooms and in vast observatories alike. What was there before the beginning? What did the universe emerge from? The scientific description, when taken seriously, offers a strange answer. It suggests that the word before does not apply. The equations of general relativity, the theory that Albert Einstein developed to explain gravity as the curvature of space and time, describe a universe in which time itself has a finite past. When those equations are traced backward, the distances between galaxies shrink, the density climbs, the temperature soars, and the fabric of space-time curves ever more sharply. Eventually, the mathematics points to a boundary where density becomes infinite and curvature becomes infinite. This boundary is called a singularity. At that point, the equations stop giving sensible answers. They do not say what lies beyond. For many cosmologists, that breakdown is not just a technical issue. It marks a horizon of understanding. On one side lies a universe filled with galaxies, stars, planets, and cold dust drifting between them. On that side, time flows, events unfold, and physical laws can be written as neat expressions that predict what will happen next. On the other side of the singularity, there is no agreed description, only hints and incomplete ideas. The word nothing often slips into that gap as a placeholder. It suggests an absolute absence, a complete void of matter, energy, space-time, and even laws. Yet this easy use of the word hides a deeper puzzle. If a true nothing has no properties at all, no potential, no structure, how could it ever give rise to anything? If the universe is here, if stars burn and atoms vibrate and thoughts appear in silent brains, then whatever preceded that activity, whatever ground allowed something to be, cannot be a simple emptiness. The idea of nothing begins to fray. The more carefully it is examined, the less stable it becomes. In the language of modern physics, even the most stripped-down concept of emptiness is no longer simple. A vacuum in quantum theory is not a clean slate. It is a restless sea of fleeting events. Pairs of particles and antiparticles appear and vanish in intervals so brief that no direct measurement can catch them in the act. Fields pervade space even when no particle is present, and those fields can store energy. If the early universe emerges from something like this quantum vacuum, then the origin story is not a leap from pure non-existence to existence, but a transition from one kind of being to another. A quiet background becomes an expanding, glowing cosmos. A latent energy turns into the matter and radiation that later divide into stars and galaxies. At the same time, general relativity insists that space and time themselves respond to energy. They are not rigid stages on which matter performs. They are part of the cast. When energy and matter appear, space stretches and time begins to flow. The birth of the universe is then not just the lighting of a fire, but the creation of the arena in which that fire can burn. The paradox intensifies. On the one hand, the universe seems to have a finite age. Observations of distant galaxies and of the faint background glow that fills the sky in every direction indicate that the cosmos has been expanding for about 13.5 billion years. On the other hand, the notion of a first moment without a before defies ordinary intuition. The mind searches for an outside, a larger frame. It wonders whether the universe could be a bubble in something greater, whether time might exist in a deeper sense beyond the timeline of this particular cosmos. In the quiet rhythm of the documentary, this tension is allowed to linger. The narrator describes a universe that begins in an instant, that is not located inside time, an expansion that does not occur in pre-existing space, but brings space into being as it grows. In this telling, the word nothing is no longer a flat wall. It becomes a thin, shifting veil between what can be described and what cannot. On one side lies a domain of measured temperatures, mapped galaxies, and tested equations. On the other lies an unknown that is not merely empty, but inaccessible. The beginning of the universe, as painted by current science, is then both solid and mysterious. Solid because many independent observations converge on the idea of a hot, dense, early state that has been cooling and expanding ever since. Mysterious because the step from no time to time, from no space to space, from no matter to matter still eludes complete explanation. The more carefully the known universe is traced back, the more sharply the edge of understanding appears. That edge is where this journey settles for now. In the stillness at the end of this first section, the cosmos hangs poised between the comfort of what is known and the vertigo of what is not. The question remains not as a failure, but as a quiet presence. How can a universe with time and space and structure arise from a state that has none of these? The answer does not arrive. The question itself becomes part of the landscape, a soft horizon at the beginning of all things. The story of the universe moves from the abstract boundary of the beginning into the first measurable instance, a realm where time exists, but is still so young that its passage can barely be imagined. Cosmologists describe these early moments not in hours or seconds, but in fractions so small that language strains to hold them, tiny slices of duration after the birth of space-time, when events unfold with a speed that defies ordinary intuition. In the first flicker after the origin, the universe is unimaginably hot and dense, a seething ocean of energy, where no atoms, no nuclei, not even stable particles can yet take shape. Temperatures reach values far beyond those found in the cores of any present star, and the energy packed into each small region of space is so intense that matter and radiation are almost indistinguishable. In this state, the cosmos is not yet a place of familiar structure, but a kind of featureless fire uniform, to a remarkable degree the same in every direction on scales that will one day span hundreds of millions of light years. This apparent smoothness poses a deep puzzle. If the universe expands from a tiny region, why does it look so even and well mixed over distances so large that light itself would not have had time to travel between them in the early epochs? To resolve this, physicists propose a brief but spectacular chapter near the very beginning called cosmic inflation. Inflation is not an explosion in space, but a sudden stretching of space itself, driven by a peculiar form of energy that acts with repulsive gravity. According to this idea, a tiny patch of space-time, perhaps smaller than a subatomic particle, enters a phase in which this repulsive energy dominates. During a time interval far less than a fraction of a trillionth of a second, this patch swells faster than any later expansion, growing from microscopic to astronomical size, while everything inside it is smoothed and flattened by the rapid stretching. In this picture, the visible universe today is just a small part of that once tiny patch expanded beyond all ordinary scales, while preserving its almost perfect uniformity. At the same time, the quantum nature of reality refuses to be completely even. Even in a state of high symmetry, there are tiny fluctuations, small random variations in the energy of the fields that fill space. During inflation, these quantum ripples are pulled to cosmic scales. Regions that were once separated by distances smaller than an atomic nucleus are wrenched apart until they stand on opposite sides of a future galaxy cluster. What begins as almost imperceptible noise becomes, after inflation ends, and ordinary expansion resumes the pattern of slightly denser and slightly thinner regions that will one day grow into galaxies and the voids between them. Thus, in the first fractions of a second, the seeds of all cosmic structure are already present, encoded in gentle variations, imprinted on an otherwise smooth background. As the inflationary phase draws to a close, the peculiar energy that drives it decays into a hot bath of particles and radiation. Space is now expanding more slowly, but it is filled with an almost uniform plasma of newly born particles, a mixture of quarks, leptons, and their antipartners, all colliding and transforming in a dense radiant fog. The fundamental forces that shape the universe begin to separate from an earlier unified state, each assuming its distinct role. The strong nuclear force binds quarks into protons and neutrons. The electromagnetic force governs interactions of charged particles, and light and gravity continues its quiet work of shaping the geometry of space-time on all scales. Time can now be counted in small but finite steps as the universe cools from unimaginable temperatures to merely extreme ones. Within a tiny fraction of a second, protons and neutrons form from the quark soup as conditions drop below a critical threshold. Moments later in this compressed cosmic timeline, these protons and neutrons begin to fuse into light nuclei in a process known as primordial nucleosynthesis. In just a few minutes of cosmic time, most of the hydrogen and helium that will ever exist in the universe is forged along with trace amounts of heavier elements. These simple nuclei drift within the still opaque plasma, waiting hundreds of thousands of years until the universe cools enough for electrons to join them and form neutral atoms. Through all of this, the scale of the universe swells. Distances between any two freely moving points increase as the fabric of space stretches, carrying the future galaxies that do not yet exist away from one another. From the perspective of much later epochs, this early acceleration and cooling is permanently written into the properties of the cosmos. The relative amounts of light elements produced in those first minutes can be calculated and compared with observations in ancient stars, an intergalactic gas providing a rare glimpse of conditions in the primordial fireball. The close agreement between calculation and measurement offers strong support for this narrative, yet the detailed nature of inflation itself remains out of reach. What exactly provides the repulsive gravity? Is it a field that still lingers in some subtle form, or was it a transient phenomenon, a phase that began and ended before any conventional notion of observation could apply? In the quiet flow of this description, the narrative returns again to what is solidly known. In the first fractions of a second, the universe transitions from a quantum-dominated state near the edge of understanding to a hot, rapidly expanding sea of particles governed by the familiar forces of physics. The smallest fluctuations in that sea are amplified by inflation into the large-scale pattern of cosmic structure, while the overall smoothness and near flatness of space emerge naturally from the enormous stretching. The universe at this stage is both simpler and more extreme than anything that will follow a young cosmos without stars or planets, but already carrying within its pattern of density and temperature the information needed for those later forms to arise. The mind that contemplates this sequence meets again the strange mixture of clarity and mystery. Equations draw a continuous line from fractions of a second after the beginning to the present day, allowing predictions about light elements and fossil radiation. Yet the very mechanism that makes the early universe so smooth and so structured at once rests on a field that has not been directly seen and on energies never reproduced in any laboratory. The cosmos seems to offer a glimpse of its childhood through careful observation, while keeping the exact nature of its earliest heartbeat concealed behind a veil that has not yet been lifted. The universe continues to cool and expand, and the blinding intensity of its first instant softens into a dense uniform glow. After the violent inflation and the brief forging of the lightest elements, the young cosmos enters a long opaque phase. Space is filled with a hot plasma of free electrons, protons, helium nuclei, and an enormous flood of photons, particles of light that collide constantly with the charged matter. In this era, the universe behaves like the interior of a star spread over all of space. Any photon that tries to cross more than a short distance is scattered by an electron absorbed and re-emitted. The cosmos is bright, but without any clear line of sight, a fog of light and matter tightly bound together. As expansion stretches space, the average distance between particles grows and the temperature falls. Over hundreds to miles of years, the fire cools from unimaginable brilliance to a still fierce but diminishing glow. Eventually, the typical photon no longer carries enough energy to knock electrons free from nuclei. A quiet but decisive transition begins. Electrons and nuclei combine to form the first neutral atoms of hydrogen and helium. Free electrons that once intercepted every photon vanish into these new atomic shells. In a relatively brief interval of cosmic time, La plasma turns into a transparent gas. In that change, a profound separation occurs. Light decouples from matter. Photons that were once trapped suddenly find that the universe has become almost clear. They begin to travel on long, nearly straight paths through space. This event fixes a kind of last photograph of the early universe, capturing its conditions at the moment when it first becomes transparent. That ancient light does not originate in stars because stars have not yet formed. It emerges from every region of space at once, a nearly uniform afterglow from the hot gas that fills the cosmos. As billions of years pass, the expansion of space stretches the wavelengths of this radiation. Each photon loses energy, sliding from visible and infrared colors into microwave frequencies far beyond human sight. Today, this fossil light fills the universe with a uniform glow at a temperature only a few degrees above absolute zero. When instruments sensitive to microwaves map the sky, they find this background in every direction almost exactly the same wherever they look. This is the cosmic microwave background, the oldest light that can be observed, a relic from when the universe is only a few 100,000 years old. At first glance, it appears extraordinarily smooth. The temperature is the same to better than a few parts in 100,000. This uniformity shows that the young universe is nearly the same everywhere as the hot Big Bang picture combined with inflation suggests. Yet the radiation is not perfectly even. Careful measurements from the ground and from space reveal tiny fluctuations in temperature, small hot and cold patches scattered across the sky. These variations are the imprints of the primordial density ripples seated in the very early universe. Slightly denser regions in the ancient plasma feel a stronger pull from gravity and compress, heating up. Slightly thinner regions expand and cool a little more. Pressure and gravity together drive waves through the gas like sound ripples in a vast glowing ocean. When electrons join nuclei and the universe becomes transparent, those waves are frozen into the pattern of hot and cold seen in the fossil light. Detailed maps of the cosmic microwave background trace this pattern. By studying how often fluctuations of different sizes appear, cosmologists read out a set of peaks and valleys that serve as a fingerprint of the young cosmos. From this pattern, they infer the age of the universe, the total amount of ordinary matter, the share of dark matter, and the presence of dark energy that drives the present acceleration of expansion. The background radiation becomes a quiet ledger recording which ingredients are present and in what proportions long before galaxies form. Yet the same map that offers such precise information also leaves questions hanging. The near-perfect uniformity across regions that appear never to have been in contact reinforces the need for a brief inflationary phase, but the exact mechanism remains unknown. Some features in the data hint at possible anomalies, alignments, or cold spots that do not sit comfortably in the simplest models. Whether these are chance quirks in a random pattern or traces of physics beyond the standard picture is still debated. As the ancient photons travel toward modern detectors, their paths are gently bent by the gravity of galaxies and clusters. This gravitational lensing slightly distorts the background pattern, adding information about how matter, both visible and dark, is spread through space. Even the faint polarization of the microwaves, the preferred orientation of their electric fields, carries clues. Certain swirling patterns in that polarization would signal primordial gravitational waves, ripples in space-time generated during inflation, and experiments continue to search for this subtle signature. For now, the cosmic microwave background stands as both confirmation and invitation. It confirms the broad outline of a universe that begins hot and dense, expands and cools with tiny quantum fluctuations growing into the structures seen today. At the same time, it invites further questions about what set inflation in motion, what lies beyond the observable horizon, and whether the faint oddities in its smooth surface are mere statistical noise or the first hints of a deeper cosmic history. The oldest light continues to bathe the universe in its steady glow, carrying across vast time the memory of the moment when the cosmos first allows light to move freely through space. When the first light of the cosmic microwave background is released and begins its long journey, the universe has already taken a decisive step from opacity to transparency. Yet in another sense it is still blind. The glow that fills space is smooth and pale, and no distinct objects break its uniformity. The cosmos has no stars, no galaxies, no fiery points of brightness. It enters a prolonged interval often called the cosmic dark ages, a time when matter drifts almost invisibly and the only illumination is the fading afterglow of its own birth, stretched to longer and cooler wavelengths by expansion. In this era, the universe is dominated by neutral hydrogen and helium gas, along with dark matter that interacts primarily through gravity. The tiny overdensities imprinted in the early plasma now begin to grow slowly under the pull of their own mass. Regions that are slightly denser than average attract more matter, becoming denser still. Regions that are slightly thinner lose material to their surroundings and become emptier. Over tens and hundreds of millions of years, this quiet competition amplifies contrasts in the distribution of matter, transforming an almost uniform fog into a landscape of knots and filaments. Dark matter leads the way. Because it does not feel the pressure of radiation or interact strongly with light, it clumps more readily, forming extended halos and threads that crisscross the universe. Ordinary gas falls into these gravitational wells, gathering into clouds whose densities gradually rise. The process is slow and largely silent. There are no bright events to mark its progress, only the steady deepening of invisible wells in the gravitational field. As the gas collects, it heats through compression and shocks, but radiative processes allow it to cool again, particularly in regions where molecules form and efficiently carry energy away. Cooling lets the gas collapse further. Within some of the largest clouds, smaller condensations emerge, seeds of future stars that form where gravity overwhelms internal pressure. The first generation of stars, called Population 3 by astronomers, is thought to be very different from the familiar suns that shine in the present universe. The pristine gas contains almost no elements heavier than helium. Without heavier atoms to provide efficient cooling, each collapsing fragment can grow more massive before it breaks apart. Simulations suggest that many of these primordial stars may reach masses tens or even hundreds of times greater than that of the later Sun. Their internal pressures and temperatures climb to extreme levels, and when nuclear fusion ignites in their cores, they shine with fierce brilliance. Yet these titans are short-lived. A very massive star burns through its nuclear fuel in only a few million years, far less than a blink on the cosmic time scale. During its brief life, it floods its surroundings with intense ultraviolet light and a wind of energetic particles, chipping away at the neutral hydrogen that still fills most of space. When the fuel in its core is exhausted, the star collapses and explodes in a powerful supernova, scattering the first heavy elements into the gas around it and sometimes leaving behind a black hole that continues to influence its environment. The emergence of the first stars marks the end of the pure dark ages and the beginning of a faint dawn. Their light cannot yet be resolved as individual points from great distances, but collectively they begin to alter the state of the universe. Ultraviolet photons from these stars have enough energy to ionize hydrogen-stripping electrons from protons. Around each early star, around each cluster of such stars, bubbles of ionized gas expand into the surrounding neutral medium. Over hundreds of millions de años, many such bubbles grow and merge, carving out large zones where hydrogen is no longer intact. This extended transformation is known as cosmic reionization. It represents a second great phase change in the universe following the first recombination that created neutral atoms. During reionization, the cosmic fog of hydrogen is gradually broken apart by light, restoring a state where atoms exist mostly as bare nuclei and electrons once again free to wander. Observations of distant quasars, the bright cores of young galaxies powered by supermassive black holes, reveal sharp absorption features imprinted by the remaining neutral hydrogen along the path of their light. By measuring how these features change with distance, astronomers trace the progress of reionization, finding that it is largely complete by about 1 billion years after the beginning. The exact timing and detailed structure of this transformation, however, remain active areas of research. Telescopes that operate in radio wavelengths aim to detect the faint signal of neutral hydrogen itself during the dark ages and the reionization era, mapping the pattern of bubbles and filaments as they grow. Space observatories like the James Webb Space Telescope search for the earliest galaxies whose combined starlight could have driven the process. Early results suggest that bright compact galaxies and perhaps the explosive deaths of massive stars contribute significantly, but the balance of sources is not yet fully settled. Throughout this long night and slow dawn, the cosmic microwave background continues to stream across space, largely unaffected but subtly modified by its passage. Some photons are scattered one last time by free electrons, created during reionization, smoothing and polarizing the fossil pattern in ways that careful measurements can detect. Those tiny adjustments provide an independent record of how much ionization occurred and when. The interplay between observation and theory weaves a narrative in which the first luminous objects are both creators and destroyers. They create structure by condensing matter into stars and galaxies, enriching their surroundings with heavy elements that will later form planets and life. At the same time, they destroy the remaining neutral hydrogen, altering the cooling properties of gas and changing how future generations of stars will form. The early universe thus passes from a simple, almost featureless state into one of growing complexity with feedback loops linking light, gas, and gravity. The mind that follows this evolution is guided from the smoothness of the background glow through the tranquil but formative dark ages into the sharp emergence of the first lights. There is a delicate balance in this story. Without the dark ages, gravity would have no time to gather matter into clouds. Without the first massive stars, the universe would remain filled with neutral gas that absorbs ultraviolet light and hinders later star formation. Too many early explosions, however, would heat and disperse the gas-delaying structure instead of promoting it. The cosmic dawn appears as a finely tuned interplay between accumulation and ignition, between the quiet work of gravity and the disruptive force of stellar fire. Yet many details remain uncertain. The precise masses of the first stars, the fraction that collapse into black holes, the role of primordial magnetic fields, and the contribution of exotic processes all lie just beyond current observation. The Dark Ages and the First Dawn are glimpsed through indirect signatures and incomplete data, like a landscape seen in silhouette before sunrise. As the section ends, the universe stands on the threshold of a more familiar era. Galaxies are beginning to assemble along the threads of the cosmic web. Stars of many sizes are forming and dying, and heavy elements are steadily accumulating in the interstellar medium. The long night is over, but the memory of that deep darkness and of the first fragile lights that pierced it remains encoded in the large-scale structure of the cosmos and in the chemical composition of everything that follows. From the first scattered islands of starlight, the universe slowly reveals a deeper pattern written on scales far beyond any single galaxy. As time passes through hundreds to millions and then billions of years, gravity continues its patient work on the small ripples in density that inflation once stretched across space. Regions that began as slightly denser patches now draw in more matter, while emptier regions surrender what little they have. Over cosmic time, this repeated gathering and draining carves a vast hidden architecture into the expanding universe, an intricate network called the cosmic web. In this web, matter does not distribute itself evenly. It flows along invisible gradients into long thread-like filaments that can stretch for hundreds of millions of light years, linking together clusters of galaxies at their intersections. Between those filaments lie wide, dark cavities, the cosmic voids where galaxies are sparse, and the average density of matter falls far below the cosmic mean. The result resembles a three-dimensional foam frozen on a scale beyond human experience, a pattern that emerges naturally from the laws of gravity acting on an initially almost uniform universe. Computer simulations of structure formation bring this process into focus, beginning with a nearly smooth distribution of matter perturbed by tiny fluctuations They let gravity pull over billions of years. What forms on the screen is a network of bright knots and filaments where matter has concentrated, surrounded by dark regions where it has drained away. When astronomers map the positions of real galaxies in large surveys and convert redshifts into distances, they see a similar picture. Clusters gather at the nodes, filaments extend between them, and vast empty expanses separate these structures like deserts between oases. Yet this visible web is only part of the story. Observations indicate that most of the mass shaping this pattern is not the luminous matter found in stars or gas, but dark matter unseen except through its gravitational pull. In simulations, dark matter provides the backbone of the web. It collapses first into halos that merge and stretch into filaments. Ordinary gas interacting with radiation and subject to pressure lags behind, but eventually falls into the gravitational wells carved by the dark component. Galaxies light up along these strands like lanterns hung on invisible wires. Evidence for this hidden scaffolding comes from the way light bends as it passes near massive structures. Gravitational lensing predicted by general relativity allows astronomers to reconstruct maps of total mass by measuring tiny distortions in the shapes of background galaxies. These maps reveal extended halosy bridges of matter that far exceed the distribution of visible galaxies, matching the predicted dark web. Even the rotation of individual galaxies hints at the same invisible presence in their outer regions. All of this points toward an architecture that not only stabilizes galaxies and clusters, but also dictates where they can form in the first place. The cosmic web, however, is not a static structure. As the universe expands, filaments continue to drain matter from the surrounding void, slowly growing more pronounced. Small halos and groups of galaxies fall along the filaments into larger structures, feeding the growth of clusters. Occasionally, two clusters approach each other along a shared filament and collide, merging into an even larger system and sending shock waves through the thin gas that permeates the space between galaxies. Observations of such collisions, in which the hot gas is displaced from the bulk of the mass, further reinforce the idea that dark matter behaves as a mostly collisionless component, passing through interactions that slow ordinary matter. In the quiet telling of this story, the cosmic web becomes more than a pattern of positions. It is a record of the universe learning how to structure itself. Tiny initial fluctuations amplified by gravity evolve into the skeleton on which all later complexity depends. The emptiness of the voids is as important as the richness of the filaments, because the contrast between them drives continued flow. Galaxies, stars, and eventually planets trace paths laid out by streams of matter that never radiate, never shine, but always pull. There is a strange humility in recognizing that the bright objects so often taken as the main actors are in a sense passengers. They ride on currents carved by an unseen sea of mass that outweighs them by a large factor. The cosmic web hints that what is most important for structure may not be what is directly visible, yet dark matter remains unidentified at the particle level. Detectors buried deep underground wait for the faintest signs of rare collisions between hypothetical dark particles and atomic nuclei. Experiments in space search for unusual signals in high-energy radiation that might betray dark matter annihilating or decaying. So far, results are inconclusive. The web is traced clearly in gravitational effects, but la naturaleza of the threads themselves is still elusive. Some proposals suggest that dark matter might not be a single particle species, but a more complex dark sector with its own interactions and structure. If so, The cosmic web would be not only a skeleton for visible galaxies, but also a stage for unseen dynamics playing out in parallel, a hidden drama whose actors leave only their gravitational footprints. As the narrative moves forward, the cosmic web stands as one of the clearest bridges between the simple initial conditions implied by the early universe and the richly structured cosmos observed today. It shows how gravity acting over long times on slight imperfections can produce a tapestry of immense scale and subtle detail, while leaving unanswered the quiet question of what truly makes up the dark scaffolding that holds it all together. Telescopes on mountains and far beyond the atmosphere now carry the story, turning the sky into a timeline. When a distant object shines, its light does not arrive instantly. It crosses space at a finite speed, so every observation is also a glimpse into the past. A modest telescope that gathers light from a nearby star looks back a few years. A large observatory that catches the glow of a remote galaxy looks back hundreds of millions or billions of years. Every mirror and detector becomes a time machine, stacking images from different distances into a layered record of the universe. On the ground, these time machines are limited by the atmosphere. Turbulent air bends and blurs incoming waves, turning sharp points into smeared patterns and hiding fine detail. Adaptive optics can correct some of this distortion, but a restless veil remains. To escape it, engineers place telescopes in orbit above the air that protects life but softens the stars. One of these orbiting instruments, named in honor of Edwin Hubble, carries a mirror a few meters across and a set of sensitive cameras. From its path around Earth, it can stare at a tiny, apparently empty patch of sky for many days, gathering every stray photon that arrives. When the image is assembled, the emptiness resolves into a field of faint galaxies, thousands of them, each a city of stars billions of light years away. These deep fields show the universe when it is much younger and more crowded, with structures still taking shape. However, the expansion of the universe steadily stretches the wavelengths of traveling light. Photons that leave early galaxies in the visible or ultraviolet part of the spectrum arrive much later as infrared light, too red for instruments tuned mainly to shorter wavelengths. To see the first galaxies clearly, astronomers need an eye that is both very cold and very sensitive to the infrared. This leads to a new observatory, the James Webb Space Telescope. Instead of a single solid mirror, it uses a mosaic of segments that unfold to form a collecting surface more than 6 meters wide. A many-layered sunshield keeps the telescope in deep cold so that its own warmth does not overwhelm the faint signals it seeks. Far from Earth, near a gravitational balance point, this observatory peers outward with an almost undisturbed view. When it examines regions of sky already imaged by its predecessor, it sees deeper and redder. Faint smudges resolve into structured galaxies. New sources appear that were previously invisible, their light stretched strongly by expansion. Some of these early galaxies seem surprisingly bright and massive given the short time since the cosmic dawn. Their stars appear to have formed quickly and in great numbers, challenging simple models in which structure builds up gently from small beginnings. Spectra taken by the telescope reveal the chemical fingerprints of elements heavier than helium in these youthful systems, implying that several generations of massive stars have already lived and died. In other cases, tiny but extremely luminous points suggest the presence of heavy black holes only a few 100 million years after the beginning, raising questions about how such massive objects can assemble so fast. Ground-based telescopes complement the view from space. On high peaks, wide mirrors gather the faint glow of distant galaxies and break it into spectra revealing motions and chemical compositions. Together with the space observatories, these instruments build a narrative from the nearby universe to epochs not long after the first stars ignite. Along this narrative, many patterns fit expectations with impressive precision, yet other findings stand out as quiet anomalies. Surveys of very distant galaxies hint that there may be more bright systems at early times than the simplest models predict. Measurements of how fast space expands made using nearby supernovae give a value that differs slightly from the value inferred using the ancient background light. This tension may be resolved by better data or more careful modeling, or it may be a clue that the standard description of dark energy, dark matter, and geometry is only an approximation to a deeper story. Each new image becomes both confirmation and question. A deep field packed with galaxies confirms that the universe is filled with structure on many scales, but it also suggests that even deeper exposures would reveal still earlier systems, perhaps so young that their stars are only just turning on. Spectra that show heavy elements in early galaxies confirm the power of massive stars to reshape their environment, but they also highlight how little is known about the detailed timing of their births and deaths. Candidates for very heavy black holes in the young universe confirm that gravity can concentrate matter with startling efficiency, yet they leave open which growth paths are used. Every telescope, whether carried by a rocket into space or bolted to rock on a mountain, therefore plays a double role. It extends the reach of human senses into earlier and earlier epochs, and at the same time it outlines the limits of observation. No matter how large a mirror becomes or how sensitive a detector grows, the horizon set by the finite age of the universe remains. Beyond a certain distance, the fog of the early plasma blocks any direct view. Beyond the point where time itself begins, observation has no meaning at all. That blank region at the start of the cosmic record is where theory must venture without direct guidance, constrained only by the echo of those earliest times that present-day telescopes can still see. The grand pattern of galaxies and the precise glow of ancient light both rest on a deeper framework, a set of equations that describe how matter and energy tell space and time how to curve. This framework, called general relativity, replaces the classical image of gravity as a distant pull with the idea that mass and energy reshape the geometry of space-time itself. Planets follow curved paths, not because something drags them, but because they move along natural routes in a warped landscape. In many tests, this theory has matched observations, and it also underlies the models of an expanding universe in which the average separation between galaxies grows with time. When these equations are applied to a universe that appears uniform on the largest scales, they compress into relations that tie together the rate of expansion, the density of matter and energy, and the overall curvature of space. These cosmological solutions lead to a startling implication. If the universe is expanding today, then in the past it must have been smaller and denser. If the expansion is traced backward in time while the rules of general relativity are kept intact, the density and temperature rise without bound. Distances between any two freely moving points shrink towards zero. Eventually, the equations predict a moment when these quantities diverge a point of infinite density and curvature. That point is the singularity associated with the Big Bang, the formal edge of the theory where its own predictions break down. A similar story appears in a different setting. When a massive star exhausts its nuclear fuel, internal pressure can no longer hold back gravity. If the star is heavy enough, it collapses inward, compressing its mass into an ever smaller volume. According to general relativity, if the mass and compactness exceed a certain threshold, the collapse produces a black hole. Surrounding it is an event horizon, a surface from which light cannot escape. Inside that horizon, the theory again predicts that the curvature of space-time grows without limit as matter falls toward a central singularity. In both cosmology and stellar collapse, the same mathematics insists on regions where the usual concept of distance and time lose their meaning. For a while, some researchers hoped that these singularities might be artifacts of special, highly symmetric models that would disappear if more realistic complications were included. Perhaps the equations misbehaved only when simplified too far. To answer this, mathematicians and physicists developed arguments called singularity theorems. These theorems do not rely on perfect symmetry or on particular kinds of matter. They show that under quite general conditions, if gravity always attracts and certain energy constraints hold any universe that is expanding, now must have had a singular beginning, and any sufficiently massive star that collapses must produce a singularity hidden inside a horizon. The equations of general relativity describe how space-time curves in response to matter and energy, and they assume that space-time can be treated as a smooth continuum at every point. Near a singularity, the curvature grows so extreme that the smooth continuum picture is no longer credible. In the regime where densities reach values far beyond anything achieved in experiments, quantum effects that are negligible in ordinary gravity should become important. Yet general relativity does not include quantum rules. Its equations march straight into a domain where they are not designed to apply, and the result is a forecast of infinite curvature. Most physicists interpret this not as a real physical state, but as a sign that the theory is being pushed beyond its range. In practical terms, this means that general relativity, for all its successes, does not by itself tell the full story of the origin of the universe or of the ultimate fate of collapsing matter. It draws the map of space-time almost everywhere, but at certain boundaries the ink runs out. The Big Bang singularity at the start of cosmic time and the inner singularities of black holes mark the edges of Einstein's map. Beyond them lies a region where a more complete theory, one that merges gravity with quantum mechanics, is required. Many attempts to construct such a theory suggest that at extremely small scales space-time may not be smooth, but granular or foamy, and that what appears as a singularity in the classical picture might be replaced by a bounce, a transition, or some more subtle structure. However, without direct experimental access to those regimes, these ideas remain speculative. Observations of gravitational waves from colliding black holes, measurements of the cosmic microwave background, and studies of the large-scale structure may someday provide indirect tests, but for now the nature of the true beginning remains concealed. In the calm rhythm of this narrative, there is a quiet unease in the idea that the main theory of gravity breaks down exactly where the most ancient questions point. The same equations that describe planetary motions and the expansion of space also insist on their own incompleteness. They lead inevitably to edges in space-time where clocks cannot tick and rulers cannot measure, where the distinction between before and after may have no meaning. At those edges, the universe withholds its first moments and its final interiors, leaving only hints in the structures that can be seen. The map is detailed and reliable almost everywhere, yet at its deep beginning and in its darkest wells it fades into blankness. There at the limits of general relativity, the story of the universe pauses, waiting for a deeper language that can speak about space-time when it is pushed beyond the smooth curves of Einstein's geometry. At the edge of Einstein's smooth map, where singularities appear and the curvature of space-time grows without limit, another description waits, one that does not treat the universe as a continuous fabric, but as something restless and granular. Quantum theory, which governs atoms, particles, and fields, insists that nothing that can be measured remains perfectly sharp. Positions, energies, and even the vacuum itself fluctuate. When this restless quantum world meets the curved geometry of general relativity, the familiar picture of space and time as a serene stage begins to dissolve. In the realm of the very small, the uncertainty principle states that certain pairs of quantities cannot both be known with arbitrary precision. If an attempt is made to define a particle's position extremely accurately, its momentum becomes wildly uncertain. Similar limits apply to energy and duration. For very short times, energy can briefly appear in excess of what would be allowed in a strictly classical picture, provided it vanishes again just as quickly. Quantum field theory turns this idea into a detailed framework describing reality as a collection of fields that fill space. Particles are excitations of these fields like ripples on a lake, and even when no real particles are present, the fields cannot sit perfectly still. They exhibit zero-point motion, fluctuating about their lowest energy state. In this view, the vacuum is not a simple emptiness, but a sea of fleeting events. Pairs of virtual particles and antiparticles appear and annihilate in intervals so short that they evade direct detection, yet their presence leaves subtle traces in measurable phenomena. Experiments that place metal plates very close together in a vacuum, for example, detect a tiny attractive force between the plates, a Casimir effect that can be interpreted as arising from the restricted modes of vacuum fluctuations between them. Such effects show that the quantum vacuum has structure and energy even in the absence of matter. When gravity is added to this restless background, a new question appears. General relativity assumes that space-time is a smooth continuum where distances and durations can shrink without limit, even if the curvature becomes extreme. Quantum theory, however, suggests that there may be a fundamental scale below which the concept of a smooth space-time loses meaning. This scale, defined in terms of universal constants like the speed of light, Newton's gravitational constant, and Planck's constant, is called the Planck scale. At lengths unimaginably smaller than those of atomic nuclei and times incomprehensibly shorter than any ordinary interval, quantum effects of gravity are expected to become dominant. John Wheeler popularizes a picture of space-time at this scale as a quantum foam. Instead of a calm, continuous fabric, space-time becomes a churning landscape where the geometry itself fluctuates. Tiny wormhole-like connections may appear and vanish. Microscopic curvatures may surge and collapse, and the distinction between separate locations becomes blurred. Just as a still pond looks smooth from a distance but reveals ripples and bubbles when examined closely, space-time may appear smooth on large scales while seething with quantum irregularities at the smallest scales. In such a scenario, the notion of a single well-defined trajectory for a particle or a definite geometry for space-time is replaced by a superposition of possibilities. To describe this properly, a theory is needed in which the gravitational field and the geometry it defines are themselves quantum objects obeying rules similar to those of other fields. Several approaches attempt to provide such a theory. One line of thought loop quantum gravity treats space-time as composed of discrete units of area and volume. In this framework, the geometry is represented by networks of finite links and nodes, and continuous space emerges only as an approximation at scales larger than the fundamental units. Close to the Planck scale, there is the smallest possible region of volume, and the infinite compression predicted by classical relativity is replaced by a finite but extreme density. Another approach, string theory, replaces point-like particles with tiny vibrating strings and sometimes higher dimensional objects. The different vibrational modes of these strings correspond to different particles, including a candidate for the quantum carrier of gravity. Because strings have a finite length, they soften interactions at very high energies, potentially smoothing out the singular behavior of classical gravity. Both approaches suggest that the classical idea of a point-like event where curvature diverges is an artifact of treating space-time as continuous down to arbitrarily small scales. A more complete quantum description may remove the singularities, replacing them with transitions or phases where the usual concept of space-time changes character. In models inspired by loop quantum cosmology, for example, the Big Bang singularity is replaced by a bounce. As the universe contracts toward extremely high density, quantum geometric effects act like a repulsive pressure, halting the collapse and reversing it into a new expansion. The current expanding universe would then follow a previous contracting phase, and the origin of time in the classical model would be a crossing point in a larger quantum history. Other ideas entertain the possibility that what appears as a beginning in classical time is actually a tunneling event from a quantum state with no classical space-time at all, or an emergence of time from more primitive, timeless degrees of freedom. In each case, the key theme is that the classical continuum of general relativity is not fundamental. It is an effective description that works exceedingly well at scales much larger than the Planck length and for curvatures that are not extreme, but it fails near the boundaries it predicts. In those regimes, the microstructure of space-time, whether pictured as loops, strings, or some other as yet unknown entities, becomes essential. The challenge is that direct experiments at the relevant energies are far beyond present capabilities. Particle accelerators cannot approach the Planck scale, and the quantum foam of space-time, if it exists, is too fine to resolve with current instruments. Instead, physicists search for indirect clues. Tiny violations of expected symmetries in high-energy particles, minute dispersions in the arrival times of photons from distant sources, or specific patterns in the cosmic microwave background could all in principle hint at underlying quantum gravitational effects. So far, no clear signal has emerged. The early universe remains one of the best laboratories for such inquiries because the densities and temperatures near the beginning approach the regime where quantum gravity should be important. Any deviation from classical behavior in that epoch might leave an imprint in the distribution of galaxies or in the statistical properties of primordial radiation. Inflation, with its amplification of microscopic fluctuations to cosmic scales, may even act as a magnifying lens for quantum gravity, stretching Planck's scale features into observable patterns. Whether such clues exist is still unknown. In the calm unfolding of this narrative, the idea of quantum foam and broken continuity gently shifts the perspective on beginnings. The Big Bang singularity is no longer a simple point where everything emerges from nothing in an instant, but a signpost indicating the breakdown of a classical description. Beyond that signpost, space-time may be grainy, fluctuating, and perhaps even fundamentally different from anything that can be pictured in everyday terms. The familiar fabric of space and time, smooth and continuous, becomes a large-scale illusion, like the apparent solidity of matter that dissolves into atoms and fields under closer inspection. What once seemed like a hard wall at the start of time turns instead into a veil of quantum uncertainty, hinting that the origin of the universe may lie in a domain where the very notions of before and after, here and there, are part of what still waits to be understood. The picture of a foaming granular spacetime opens the door to a different way of thinking about the beginning, one in which the Big Bang is not a unique creation event, but a transition between phases. Among the attempts to merge quantum principles with gravity, one line of work focuses on the geometry itself, treating space and time as composed of discrete units. In this approach, often called loop quantum gravity, the smooth fabric described by general relativity is replaced at very small scales by a network of tiny loops. Areas and volumes can take on only certain minimum values, much as energy levels in an atom come in discrete steps, so space becomes a kind of lattice, made not of points, but of finite chunks woven together. Applied to the cosmos as a whole, these ideas lead to a simplified scheme known as loop quantum cosmology. Instead of quantizing every possible shape of space-time, the theory begins with a symmetric model of the universe similar to the one used in standard cosmology and imposes quantum rules on the few remaining degrees of freedom. The resulting equations resemble those of general relativity on large scales, but they change character when densities approach the Planck regime. In the classical description, the density of matter and the curvature of space-time grow without bound as the Big Bang is approached. In the loop-inspired picture, the discreteness of geometry introduces a new effect. When density and curvature rise toward a critical value, quantum geometric pressure appears acting against further compression. Instead of allowing the scale of the universe to shrink to zero, the equations predict that contraction slows, halts, and reverses. The singularity is replaced by a bounce. A universe that is collapsing under its own gravity rebounds into a new expanding phase. In this scenario, the Big Bang is not the absolute beginning of everything. It is the moment of minimum volume in a longer history that includes a previous universe in contraction. Time continues through the bounce, even if conditions near that pivot are so extreme that ordinary matter is transformed into exotic states. The idea of a bounce resolves the specific problem of the Big Bang singularity within the scope of the model, but it also raises new questions. If there was a previous universe that contracted what set its initial conditions, is there an endless chain of expansions and contractions, each linked by quantum bounces, or does the sequence have a limit? Does the entropy, the measure of disorder that tends to increase in closed systems, reset or evolve in some subtle way across the bounce? These questions touch on whether time has a beginning at all, or whether the notion of a first moment is only a feature of the classical approximation. Loop quantum cosmology also suggests that the bounce might leave imprints on observable quantities. The same microscopic discreteness that produces the repulsive effect at high density may modify the behavior of fluctuations in the early universe. If inflation occurs after the bounce, the small quantum variations in geometry and matter that emerge from the contracting phase could be stretched and amplified. Tiny differences from the predictions of standard inflation might appear in the pattern of temperature fluctuations in the cosmic microwave background, especially on the largest angular scales. Some studies claim that features such as a slight suppression of power on very large scales or particular correlations between modes might hint at a pre-Big Bang phase. So far, however, the data are not decisive. The observed features can often be explained within simpler models, and statistical uncertainties remain. The bounce, therefore, sits at an intersection between theory and observation. It offers a mechanism to avoid an initial singularity and potentially links that mechanism to measurable consequences, yet the evidence is still subtle. Other bouncing models not based on loops explore similar themes by altering the matter content of the universe or modifying gravity at high curvature so that the scale of the cosmos oscillates rather than beginning from zero. In these pictures, the universe passes through cycles of growth and recollapse, and the Big Bang becomes one note in a longer rhythm. Without direct access to Planck's scale, physics' many different forms can be written that soften or eliminate the singularity, and each must then be tested against observation. In the quiet flow of the documentary, the Big Bounce idea reshapes the contour of the origin story. The sharp edge of a universe emerging from an absolute beginning is softened into a turning point in a larger process. The image of time as a line with a marked starting dot gives way to a curve that bends back on itself, or to a loop in which each pass through extreme density seeds the next expansion. The sense of mystery does not diminish, it changes focus. Instead of asking how something emerges from nothing, the mind is invited to ask how an extended sequence of phases might be organized, and what, if anything, selects the specific properties of the present cycle. Even if future observations disfavor particular bouncing models, the singularity at the Big Bang no longer appears as an unmovable wall. It becomes a signpost pointing toward the limits of classical understanding and suggesting that the true structure of cosmic history may involve processes in which space, time, and matter undergo transformations that are only beginning to be imagined. The bounce turns into a symbol for this possibility, a reminder that what appears as an absolute beginning from one perspective may be from another only a moment of passage in a deeper ongoing story. Roger Penrose brings a different perspective to the question of beginnings, one that does not rely on a bounce through a dense phase, but instead stretches the story of the universe into a chain of linked eras. In his vision called conformal cyclic cosmology, the universe does not have a single origin and a single end. Instead, it passes through successive eons, each one a complete cosmic history, from a hot early state to a cold diffuse future. The end of one eon becomes the beginning of the next, and what appears as a Big Bang in ordinary cosmology is in this picture a transition rather than an absolute creation event. The key lies in how the geometry of space-time can be rescaled without changing the paths of light. In general relativity, multiplying the metric by a smooth factor preserves the structure of light cones, a rescaling called a conformal transformation. Penrose notices that at the very beginning of a hot Big Bang universe, and at the very end of an ever-expanding universe filled only with radiation, the detailed scales of time and distance may lose their meaning. At the initial singularity, densities become so high that the distinction between small and large blurs. At the cold future, massive particles decay or are swallowed by black holes, which themselves evaporate over immense timescales, leaving behind almost pure radiation. In such a late state, with no mass to define clocks and rulers, the precise size of the universe again becomes unimportant. In this limit, he proposes the remote future of one eon and the initial state of the next can be related by a conformal mapping that compresses the endless future of the old universe into a finite boundary identified with the Big Bang of the new aeon. Time in each aeon flows from its own Big Bang like beginning to its own cold radiation-dominated end, but the collection of eons forms an endless chain joined at these conformal boundaries. This picture removes the need for a single absolute origin, yet it introduces a different kind of mystery. For it to work, the entropy associated with gravitational degrees of freedom must be extremely low at the start of each aeon. In standard cosmology, the smoothness of the early universe already poses a puzzle. Thermal entropy is high because radiation and matter fill space almost uniformly, but gravitational entropy, which measures how clumped the gravitational field can become, is low because the mass distribution is so even. Over time, as structure forms, black holes appear and grow, and the gravitational entropy increases dramatically. In the conformal cyclic picture, the evaporation of those black holes in the far future removes this high gravitational entropy, leaving behind a nearly uniform sea of radiation. Without mass, the universe forgets its own scale and can be conformally shrunk to a smooth boundary. That boundary then plays the role of a new Big Bang with low gravitational entropy for the next aeon. Penrose suggests that traces of previous aeons might still be visible in the present one. When very massive black holes merge in the aeon before ours, they release bursts of gravitational radiation. As that aeon ages and its black holes evaporate, the gravitational waves continue to cross the thinning cosmos. In the conformal mapping to the next aeon, these waves become features imprinted in the initial conditions of the new universe. When matter and radiation fill space again after the hot early phase, these imprints could appear as subtle circular patterns in the temperature variations of the cosmic microwave background. Some analyses of background data have claimed possible signs of such circles regions where the variance of the temperature fluctuations is slightly lower than average arranged in concentric rings. Other studies argue that these patterns are consistent with random noise. The debate continues with no consensus yet on whether any observed features truly support the conformal cyclic picture. Beyond these specific signatures, conformal cyclic cosmology raises wider questions about the meaning of time and scale. In each eon, local physics proceeds according to familiar laws. Stars form galaxies, evolve black holes, accumulate and transform matter. Yet the overall narrative has no first moment and no final end. Instead of a line with a marked starting point and an arrow pointing toward heat-death time becomes a succession of chapters each written on a canvas prepared by the erasure of the previous one. The low gravitational entropy at each Big Bang is no longer an unexplained initial condition, but a consequence of the previous eon having emptied itself of massive clumps. Still, this elegance sits beside unresolved issues. The detailed behavior of fields across the conformal boundary, the treatment of dark energy in late eons, and the requirement that all rest mass vanish in the far future depend on assumptions that have not yet been confirmed. In the calm unfolding of this narrative, Penrose's sequence of eons offers a different way to soften the singular beginning. It does not replace the Big Bang with a bounce through a dense phase, but with a transformation in which scale loses meaning, allowing the end of one universe to be reinterpreted as the beginning of another. The cosmic microwave background becomes, in this view, not just the afterglow of a single birth, but possibly a palimpsest, carrying faint reminders of worlds that came before. Whether or not future data support this vision, the idea that the universe might be part of an eternal procession of eons expands the horizon of imagination, and the apparent starting point of time in ordinary cosmology becomes one link in a chain whose full extent remains hidden. The idea that the universe begins in a single explosive event is powerful, but some theorists wonder whether reality might be less like a solitary firework and more like a sequence of pulses. In this view, the Big Bang is not a lone, unrepeatable act, but one of many episodes in which new energy and new structure enter the cosmos. Instead of a smooth, gradually slowing expansion driven by a fixed set of ingredients, the history of space may be punctuated by discrete bursts, mini bangs, that leave behind subtle marks in the pattern of galaxies and in the rate at which the universe grows. The standard cosmological picture describes how an initial hot, dense state expands and cools with dark matter and dark energy treated as stable components. Dark matter shapes the formation of structure through gravity, while dark energy acts as a nearly constant background pressure that accelerates the expansion. This model fits a wide range of observations, yet some measurements hint that the expansion history of the universe may not be perfectly smooth. Large surveys that chart millions of galaxies suggest that the acceleration driven by dark energy may have varied slightly over cosmic time, as if LA push on space-time has changed strength in gentle stages rather than along a perfectly simple curve. This has led to speculative models in which dark energy is not a fixed constant but a dynamical field that can change, stiffen, or relax. In some versions, each change corresponds to a miniature creation event, a brief injection of energy into the vacuum that behaves like a small echo of the Big Bang. These mini-bangs do not shatter existing structure. They act instead like soft pushes on the fabric of space-time, altering the overall rate at which galaxies recede from one another. In such a scenario, the universe is not created all at once, but is continuously fed by the underlying quantum vacuum. Occasionally, fluctuations in that vacuum could cross a threshold, triggering a short phase of rapid expansion or an adjustment in the properties of dark energy. Once the field settles into a new state, the universe continues to expand under slightly different rules. Over billions de años, these steps could accumulate into a complex expansion history with quiet epochs separated by subtle shifts. Some models go further, imagining that each mini-bang corresponds to the nucleation of a bubble with slightly different physical parameters. Within a single overarching space-time, multiple domains might exist, each born from its own pulse of vacuum energy, each with its own version of the constants that govern matter and forces. In this multi-region view, the observable universe is one bubble among many, shaped by the particular pattern of mini-bangs that have occurred in its past. Though such ideas are highly speculative, they arise naturally when quantum field theory is applied to a landscape of possible vacuum states. The key question is whether any direct evidence could distinguish a universe that experiences multiple small creation-like events from one that evolves smoothly after a single Big Bang. One possible clue lies in the detailed pattern of galaxy clustering. Mini-bangs that occur long after the earliest phases would subtly change the distance scale at which features appear, introducing gentle kinks into the relation between redshift and distance. Another potential signal could be found in the statistics of very distant supernovae, which act as standard candles for measuring expansion. A sequence of small jumps in the dark energy density might leave behind faint imprints in the brightness pattern as a function of cosmic time. Current data are not yet precise enough to confirm or rule out such fine structure in the expansion history, but upcoming surveys aim to map many more galaxies and many more supernovae, sharpening the view of how space has grown. There is también the question of how these pulses would interact with the early universe. If some mini-bangs occur before or during inflation, they might modify the spectrum of primordial fluctuations, adding or suppressing power on certain scales. The cosmic microwave background with its detailed pattern of hot and cold spots becomes a sensitive canvas on which even small departures from the simplest models might be painted. To date, the observed pattern agrees well with a single inflationary episode followed by smooth expansion, but a slight tension between different measurements of the expansion rate keeps the door open to more complex histories. In the gentle pacing of this narrative, the concept of many mini-bangs introduces a new flavor of mystery. It shifts the focus from an origin question framed as once and for all to a process question framed as again and again. Instead of asking only how a universe can arise from an initial state, the mind is invited to consider whether creation in a broad sense might be ongoing. The vacuum, no longer a passive background, becomes a participant that can occasionally rearrange itself and in doing so subtly rewrite the rules of cosmic evolution. Whether the universe truly carries the scars of such pulses is unknown, but la possibility underscores how much remains to be learned about dark energy, the quantum vacuum, and the way they shape the large-scale fate of everything. The single Big Bang remains the central pillar of modern cosmology, yet around it grows a halo de ideas in which the history of expansion is more segmented, more intricate, and perhaps more surprising than a simple smooth curve would suggest. Beneath the luminous web of galaxies, clusters, and glowing gas, a deeper structure exerts a silent control. This hidden component called dark matter does not shine, absorb, or reflect light in any known way, yet its gravitational influence shapes the universe from the smallest galactic scales to the largest cosmic patterns. The evidence for its presence emerges, gradually accumulating from many directions until the invisible becomes impossible to ignore. One of the earliest clear signs appears in the rotation of spiral galaxies. When astronomers measure how fast stars and gas orbit around the center of a galaxy, they expect the speeds to drop at large radii, much as planets in the outer solar system move more slowly than those close to the Sun. The visible mass of a galaxy is concentrated in its bright central bulge and spiral arms. According to Newtonian gravity, orbital speeds should decline once most of the mass lies inside the orbit. Instead, observations show that stars far from the center move almost as fast as those nearer in. The rotation curves flatten rather than fall. This behavior implies that the total mass within those outer orbits continues to grow with radius, even though the amount of visible matter does not. The most straightforward interpretation is that each galaxy is embedded in an extended halo of unseen matter far more massive than the luminous disk. Independent lines of evidence point in the same direction. Galaxy clusters, the largest gravitationally bound structures, contain thousands of galaxies, along with hot gas that emits bright X-rays. By measuring the motions of galaxies inside the cluster and the temperature of the gas, astronomers can estimate the total mass required to keep the system bound. In cluster after cluster, the necessary mass exceeds what can be accounted for by stars and gas alone. Something else must provide the additional gravity. Gravitational lensing offers an even more direct view. When light from distant galaxies passes near a massive foreground object, the curved space-time bends its path. Background galaxies appear slightly stretched, distorted, or multiplied into arcs and rings. By analyzing these distortions across a region of sky, researchers can reconstruct a map of the total mass regardless of whether it emits light. In some dramatic systems where two clusters have collided, such as the so-called bullet cluster, the hot gas, slowed by the collision, separates from the main mass peaks, which are traced instead by lensing. The mass follows the galaxies, not the gas, indicating that most of it behaves as a nearly collisionless component, very much like a cloud of invisible particles that pass through one another. On the largest scales, the imprint of dark matter appears in the pattern of temperature fluctuations in the cosmic microwave background and in the distribution of galaxies across space. The tiny variations seen in the ancient light encode how fast different scales of density fluctuations can grow under gravity. Without a dominant dark matter component that does not feel radiation pressure, those fluctuations would not have enough time to grow into the rich cosmic web seen today. Simulations that include only ordinary matter fail to produce the observed level of structure. When dark matter is added as a cold, slowly moving component, the simulations naturally generate filaments, clusters, and voids that resemble the real universe. All of these clues converge on a picture in which dark matter makes up about 5 times as much mass as ordinary atoms. It forms extended halos around galaxies and clusters and provides the gravitational backbone of the cosmic web. Yet its exact nature remains one of the deepest open questions in physics. The leading idea is that dark matter consists of some new kind of particle that interacts very weakly with ordinary matter and with light, but participates fully in gravity. Many hypothetical candidates have been proposed. Weakly interacting massive particles, sometimes imagined as relics from high-energy processes in the early universe, could have the right abundance and behavior. Ultralight axion-like particles arising from certain extensions of known theories might also account for the observations forming a kind of diffuse wave like dark fluid. Sterile neutrinos, additional versions of the known neutrinos that do not feel the usual weak nuclear force, have also been suggested. To search for these possibilities, experiments take several approaches. Deep underground laboratories house large detectors filled with ultra-pure materials in which a rare collision between a dark matter particle and an atomic nucleus might produce a tiny flash of light or a faint electrical signal. Space-based instruments look for unusual patterns in cosmic rays or gamma rays that could arise from dark matter particles annihilating or decaying. Particle colliders attempt to create dark matter in high-energy collisions where it would reveal itself only as missing energy and momentum. So far, none of these searches has produced a definitive detection. Each null result narrows the range of possible properties, but the underlying mystery persists. It is also possible that the interpretation of the data in terms of unseen particles might need revision. Alternative ideas propose that the laws of gravity themselves change at very low accelerations or on very large scales, reducing or eliminating the need for dark matter. Modified gravity theories can sometimes reproduce the rotation curves of individual galaxies with fewer additional assumptions, but they often struggle to match the full range of evidence, especially the behavior of clusters and the detailed structure of the cosmic microwave background. In the calm unfolding of this narrative, dark matter stands as both a stabilizing presence and a source of enduring intrigue. It stabilizes galaxies, allowing their fast-rotating disks to remain intact. It anchors clusters, preventing them from flying apart. It sculpts the cosmic web, providing the framework on which ordinary matter condenses into stars and planets. At the same time, it refuses to reveal its inner identity, appearing only through the way it bends light and guides motion. The luminous universe, with all of its colors and shapes, turns out to be a minor component floating in a sea of something that does not shine. The thought that most of the matter in existence is invisible and unknown shifts the sense of what is familiar. The bright spiral arms of a galaxy become surface foam on a deep black tide. Every star, every planet, every atom is a trace element in a cosmos whose dominant substance has yet to be directly touched. The invisible architecture holds everything in place, but the blueprint of its composition remains locked away, waiting in the gentle pull of orbits and in the faint distortions of distant light for a future insight that might finally give it a name beyond the simple phrase, dark matter. The invisible mass that holds galaxies together is only part of the unseen story. On even larger scales, another hidden ingredient appears to push them apart. This component, called dark energy, does not simply sit in halos or filaments. It seems instead to be spread throughout space itself, acting as a gentle but persistent pressure that accelerates the expansion of the universe. The discovery of this acceleration near the end of the 20th century changes the view of cosmic history in a profound way. Before, many cosmologists imagined that the mutual gravity of all matter might slow the expansion over time, perhaps bringing it to a halt or even reversing it into contraction. Measurements of distant galaxies show that the universe is indeed expanding, but the expectation is that this rate should steadily decrease. Then observations of very distant Type 1 supernovae exploding stars that serve as standard candles reveal that those galaxies are dimmer than they would be in a purely decelerating universe. The light has traveled farther than expected, implying that the expansion has sped up in recent cosmic time. Instead of coasting or slowing, space appears to be stretching faster and faster. To account for this, one simple possibility is to reintroduce a term that Albert Einstein once included in his equations of general relativity and later set aside the cosmological constant. This term behaves like a fixed energy density of empty space. Unlike ordinary matter or radiation, whose density thins as the universe expands, a cosmological constant maintains the same density everywhere. As space grows, the amount of this vacuum energy increases in proportion to volume. Its effect on the geometry of space-time is repulsive at large scales, driving accelerated expansion. In this picture, dark energy is simply this constant vacuum energy, a property of space that does not change over time. Yet this solution, though mathematically straightforward, carries a deep puzzle. Quantum field theory predicts that the vacuum should possess a large energy density from zero-point fluctuations of fields. The actual dark energy density is incredibly small by particle physics standards, but also non-zero. The question of why it has this tiny value and not zero, or the much larger quantum estimate, stands as one of the sharpest mismatches between theory and observation. To ease this tension, some physicists propose that dark energy is not a simple constant but a dynamical field often called quintessence. In such models, a scalar field permeates space, slowly rolling down a potential energy landscape. Its value and energy density can change with time, gently altering the rate of expansion. Observationally, dark energy is often summarized by its equation of state, the relation between its pressure and its energy density. A pure cosmological constant has a specific fixed relation. Quintessence models predict values that differ slightly from this and perhaps vary over time. By combining data from supernovae, the cosmic microwave background, and the large-scale distribution of galaxies, cosmologists attempt to measure this relation with increasing precision. So far within uncertainties, dark energy behaves very much like a cosmological constant, but the error bars still leave room for small departures. Subtle tensions between different measurements of the current expansion rate also hint that the standard model may be incomplete, though systematic errors may yet resolve these disagreements. The presence of dark energy reshapes the long-term forecast for the universe. Without such a component, the fate would be determined primarily by the total density of matter, with expansion either slowing toward recollapse or coasting ever more gently outward. With dark energy dominating, the picture is different. As the universe ages, matter becomes ever more diluted, while the dark energy density remains roughly constant. Eventually, dark energy comes to vastly outweigh all other forms of energy. The expansion then approaches an exponential phase in which distant galaxies are carried away beyond the horizon, their light redshifted until it fades below any possible detection. On sufficiently long timescales, each bound structure, such as a galaxy group, becomes effectively an isolated island in an ever faster rushing void. The idea that empty space has an energy that can drive cosmic acceleration also deepens the connection between the smallest and largest scales. The same quantum fluctuations that ripple through the vacuum at microscopic distances seem to play a role in aggregated form in shaping the geometry of the entire universe. Yet the gap between theoretical estimates and the observed value suggests that some critical piece of understanding is missing. Perhaps a symmetry yet to be discovered cancels almost all of the vacuum energy. Perhaps contributions from different fields finally balance. Perhaps the observable universe is one region in a larger multiverse where the vacuum energy takes many possible values, and only in regions where it is small can complex structures arise. In the calm tone of this narrative, dark energy stands as a quiet but decisive agent. It does not burn, collide, or clump. It does not form stars or planets. It acts instead as a background influence that becomes dominant only when the universe has expanded and thinned sufficiently. Its presence is inferred not from local experiments, but from the way vast stretches of space evolve over billions of years. The rushing apart of galaxies, the accelerating redshift of ancient light, and the increasingly empty cosmic horizon all point toward a reality in which the vacuum itself exerts a gentle push. This push is measured, yet its origin remains obscure, a reminder that the space between things is not truly empty, but holds within it one of the most profound mysteries in contemporary cosmology. The presence of dark energy leads naturally back to an older question that has changed shape many times, the question of what empty space really is. Classical intuition pictures a vacuum as pure absence, a stage cleared of all particles and fields and nothing in which something might later appear. Modern physics, however, has steadily eroded this simple image. The more precisely the vacuum is examined, the less empty it becomes. It behaves less like a void and more like a medium, subtle and invisible, that can store energy, fluctuate, and even give birth to particles under the right conditions. Quantum field theory replaces the idea of individual particles moving through a mute background with a set of fields that fill all of space. Electrons, photons, quarks, and every other known particle correspond to excitations of underlying fields as ripples correspond to waves on a lake. The state with no particles present is not one in which the fields vanish, but one in which they sit in their lowest energy configuration. Even there, uncertainty forbids perfect stillness. The fields jitter with zero-point motion, and these restless fluctuations exist everywhere all the time. In some circumstances, the effects of these fluctuations become visible. When two metal plates are placed very close together in a vacuum, fewer modes of the electromagnetic field fit between them than outside. This imbalance in allowed fluctuations creates a tiny net force that pushes the plates together, a Casimir effect that shows directly that the vacuum contains active degrees of freedom even when no real photons are present. Similar reasoning underlies small shifts in atomic energy levels where interactions with vacuum fluctuations slightly alter spectra. These signatures reveal that the vacuum is structured, not blank. If the vacuum has fluctuating fields, it also has an associated energy. In quantum field calculations, the contributions from all possible modes pile up to an enormous value far larger than anything compatible with the gentle cosmic acceleration attributed to dark energy. This clash between the huge theoretical vacuum energy and the tiny observed dark energy density is one of the sharpest mismatches between theory and observation. Yet another perspective softens the contrast. The absolute value of the vacuum energy may be less important than its effect on the curvature of space-time. Perhaps unknown mechanisms or symmetries cancel almost all of the quantum contributions, leaving a small residual. In that case, the dark energy that governs the expansion might be the faint remaining trace of the same vacuum fluctuations that rearrange atomic spectra and push metal plates together. Regardless of the exact resolution, the link between vacuum structure and cosmic behavior tightens. Space, even when emptied of ordinary matter and radiation, retains the potential to influence motion, bend light, and guide the growth or slowing of the universe itself. In extreme environments, the vacuum shows another face. Near the horizon of a black hole, quantum fields experience strong gravitational gradients. Virtual particle pairs that normally annihilate almost instantly can be separated, with one partner falling into the hole and the other escaping as real radiation. This Hawking process slowly drains energy from the black hole, converting curved space-time geometry into particles that stream away. The interplay between vacuum energy and expansion also takes on a central role. Inflation is often modeled as a period when a scalar field sits in a high-energy vacuum-like state, dominating the energy budget and acting as an almost constant dark energy. As the field rolls down to a lower energy configuration, the effective vacuum energy decreases, the inflationary phase ends, and the stored energy converts into a hot bath of particles. In this story, the difference between two vacuum states, rather than the absolute energy itself, sets the stage for the hot Big Bang. The vacuum becomes a landscape with plateaus and valleys, and cosmological history is a path through that terrain. Some speculative ideas suggest that this landscape might be broad, with many possible vacuum states corresponding to different values of physical constants. Even without invoking multiple regions, the local vacuum is already rich. It carries zero-point energies, permits virtual pairs, responds to boundaries, and couples to gravity. It can be polarized by strong fields and may undergo phase transitions as conditions in the universe change. The quiet background becomes a restless medium whose properties set the stage for every process that unfolds within it. In the gentle pace of this narrative, the vacuum is revealed as the closest physical counterpart to the philosophical idea of nothing, yet it refuses to be nothing. It is everywhere and nowhere, invisible, yet measurable, simple in concept, yet intricate in behavior. It blurs the line between absence and presence, suggesting that what is thought of as empty space is in fact a reservoir of latent possibility. When the universe expands, it is this structured vacuum that stretches. When dark energy accelerates the expansion, it may be the tiny imbalance of vacuum contributions that exerts the push. When particles appear, radiate, or decay, they do so against a backdrop that is never fully still. The origin of the universe, when traced back through inflation and beyond, thus intertwines with the origin of the vacuum itself. To approach how something can arise from apparent nothingness, it is necessary to understand what the vacuum really is, how its fluctuations, energies, and possible phases relate to the geometry of space-time. For now, the vacuum stands as a paradoxical entity, both the simplest state and a source of deep complexity, quietly filling all of space while holding within its structure many of the unanswered questions about why the universe has the form that it does. As the narrative threads of expansion, structure, dark components, and quantum foam weave together, a quieter theme emerges beneath them all: the nature of time itself and how far back its meaning can stretch. Every observational story told by telescopes and detectors assumes a background in which events can be ordered one after another along a line of before and after. Supernovae explode, galaxies collide, stars are born and die, and the record of their light arrives in a sequence that can be arranged on a cosmic timeline. General relativity encodes this ordering in the geometry of space-time, where light cones define what can influence what, and where the curvature of the manifold tells clocks how to tick. In such a picture, causality is not an external rule layered onto events. It is built into the structure of space-time itself. Yet when this framework is pushed toward the earliest moments of the universe, the very assumptions that support a clear causal order begin to erode. In the familiar eras after the cosmic microwave background forms, the universe is transparent and light carries information freely. Horizons define which regions can exchange signals in a given time. The particle horizon marks the maximum distance from which light could have reached a given observer since the beginning of expansion. Beyond it lie regions that are for practical purposes causally disconnected. Inflation stretches a tiny region to cosmic size, making parts of the sky that appear far apart today trace back to a single once connected patch. This solves the puzzle of their similarity, but introduces a new sense of isolation. If inflation continues elsewhere, vast domains may exist forever out of causal contact, separated by inflating space that no signal can traverse. Causality becomes local, tied to particular pockets where inflation has ended, while the global structure grows tangled in ways that cannot be fully mapped from within any one region. Even within the observable universe, there are limits. Future event horizons appear in models dominated by dark energy. As accelerated expansion continues, there comes a time when light emitted from sufficiently distant galaxies can never reach certain worldlings. Those galaxies recede beyond a horizon defined not by a solid boundary, but by the interplay of expansion and light speed. In such a universe, every bound group of galaxies eventually finds itself surrounded by an expanding void that information cannot cross. The causal fabric frays at large scales, leaving isolated islands of interaction in a sea of unreachable regions. In this setting, the question of an origin acquires an added subtlety. The Big Bang is often imagined as a moment when everything is concentrated at a single point, but in the geometrical description, it is more accurate to think of it as a boundary in time, a surface in the four-dimensional manifold to which all past-directed time-like and light-like curves converge. That boundary is not an event inside time. It is the edge of the time dimension itself, beyond which the equations of classical relativity do not extend. Asking what happened before that boundary is like asking which event lies earlier than the earliest point on a line that has a beginning. The mathematical structure simply does not provide such points. This does not settle whether some deeper description might extend the line as bouncing models or cyclic eons suggest, but it shows that within the standard framework, the concept of a cause for the beginning has no place to attach. Cause and effect require a temporal order where no time parameter exists. The ordinary idea of cause dissolves. Quantum cosmology complicates this picture further. Some approaches describe the universe not as evolving within a pre-existing time, but as a whole quantum state. In certain formalisms, time emerges only in an approximate way when the quantum state is decomposed into parts that can play the role of a clock and a system. In such views, asking what came before the universe may be as ill-posed as asking what lies north of the North Pole. The origin is not an earlier event, but a change in description from a timeless quantum object to a classical space-time, where time becomes a meaningful coordinate. The boundary at the Big Bang becomes a surface where one language gives way to another, not a point in a larger chronological chain. Philosophically, this challenges deep intuitions. Human experience is steeped in temporal sequence. Memory records the past and anticipates the future. Every object encountered has a story that stretches back through causes and forward through effects. The mind instinctively extends this pattern to the universe as a whole, seeking a prior condition for every state, a prime mover for every motion. Cosmology reveals that this habit may not apply at all scales. The combination of a beginning and classical time horizons that restrict causal contact and quantum descriptions in which time is not fundamental suggests that explanation itself has limits anchored in the structure of reality. The horizon that bounds what can be known is not only physical drawn by light cones, but conceptual drawn by the domains in which familiar ideas like cause, event, and sequence hold. Still, the scientific account does not end in a simple declaration of unknowability. Instead, it frames the unknown in concrete ways. The early universe leaves measurable traces in the cosmic microwave background, in the abundances of light elements, and in the large-scale distribution of galaxies. These relics constrain which models of the beginning are viable. Some scenarios with bounces multiple eons or mini-bangs predict specific subtle deviations in these relics, and observations can rule out or support them. The boundary at the start of classical time is not an arbitrary barrier. It is a surface woven from data and theory, one that can be approached asymptotically even if it cannot be crossed. In the calm closing of this long arc, time itself appears as part of the mystery it was meant to illuminate. The universe expresses a history that stretches back through stars and galaxies to a hot, dense state, and perhaps through bounces or cycles or quantum transitions beyond that. Yet in every version there is a horizon beyond which familiar categories fail. Whether that horizon hides a previous phase or marks the emergence of time from a timeless substrate, it stands as a gentle reminder that not every why has a deeper why, and not every before has a further before. The origin of the universe in this light is not a single answer waiting at the end of all questions, but a boundary where explanation gives way to wonder, and where the flow of time so present in every heartbeat and every orbit touches something that lies quietly outside its reach.